Thank you for allowing us to present on reducing residential water consumption using feed-forward process control. Water is a precious resource, especially in the western and southwestern United States. According to the Washington Suburban Sanitary Commission, each household uses 400 gallons a day for yard irrigation. We believe that we can be more efficient in our water consumption in this area. We realize that many homeowners already have a sprinkler system in place, but it's our hope by the end of this presentation that you'll be more open to implementing our idea. Our objective is to create a controller that will reduce water consumption while still allowing for healthy grass growth. May we now begin our presentation.
To accomplish our objective, we started by deriving a first principles model for the amount of water in the soil. We did this by doing a species mass balance for the amount of water in the control volume shown in the figure. The equation we came up with was the changing the amount of water with time is the amount of water coming in through the sprinkler and the rain minus the amount leaving through convective mass transfer. In the figure, the purple variables are input variables, which we obtained from the National Climatic Data Center, and they're available for every 5 minutes throughout the day, and they affect the convective mass transfer. So we linearize the equations and put them in deviation variable form to get transfer functions and that's the equation, the linearized equation. And next we implemented our model in Simulink and Matlab and designed a custom controller that would only water when a minimum amount of water in the soil was met to save on the amount of water used. And finally we implemented a standard watering regime into Simulink so we could compare our controller with, have something to compare our controller with.
There are three main results of our project. The first is that the controller is able to reduce the amount of deviation that the amount of deviation in the soil moisture levels, and that's shown with the first graph at the top. The red line represents normal watering practices, and the blue line is our controller. And this accounts for any changes in ambient conditions such as air temperature and wind speed. The deviation is especially influenced by the amount of rainfall, as can be seen in the second graph. The red line steadily increases because normal watering will water every day regardless of the amount of rainfall, whereas the controller will adjust and account for that rainfall. This controller greatly reduces the amount of water used through water irrigation, and the potential water savings is 24,000 gallons per household each year according to our model and simulation. And while financially this may not be very significant for an individual household, when it is applied to a larger scale, there are significant savings in water and cost. One advantage to using the controller is the possibility to retrofit the programming onto existing sprinkler systems, and then it would be able to import real-time data for temperature and wind speed in order to minimize the amount of water used. Another advantage is that because there would be practically no hardware costs associated, there would be large savings for installation. Some recommendations for future work include refining the process model so that it better fits and includes experimental data, and that it will include different forms of evaporative mass transfer. Another possibility is to account for different soil and grass types in order to make a controller that is specific to different geographical regions. Thank you for your time and your interest in reducing water consumption through process control. Thank you.